Perfect. Hear you well.
Awesome. Thank you.
Thanks. And you have a second person with you, is that right?
She is teaching, so I have a recorded presentation for her today.
Okay,
So I'll
great.
go first and then I'll play the video and hopefully that comes through on Zoom okay.
That's great. Thanks, and I'll turn things back off to Louis.
Can you see me and hear me well?
Yes,
Okay.
perfect.
My name is Luisa. I'm a RIS fellow. I'm also a student of the Sustainability Studies Master at the Lenoran University. I'm from Colombia. I've been living here in Nashville for 3 years, and I'm so happy to be able to share this space with you. Oh, sorry for the noise. At this place is so noisy. Okay, so right now the speakers that we have are Dr. Courtney Di Vittorio. She's an assistant professor of engineering at the Wake Forest University, and she's a professional engineer and an assistant professor too. She earned a PhD in civil engineering for the Georgia Institute of Technology, and her research broadly focuses on developing new data sets and models that can support the stakeholders managing complex and uncertain hydrological systems. So she's going to be able to talk to us about all these interesting topics and about how to how to manage a low-cost water quality monitoring system. And also we'll have Dr. Kyana Young. She's an assistant professor in the Department of Engineering at Wake Forest University too. Her research focuses on water treatment and public health, where her work has included water treatment technology projects in Haiti, Sierra Leone, China, India, and Hong Kong. And she's currently the co-chair of the Water and Health Committee and at a governing council in the environment section with the American Public Health Association. Dr. Young is also the co-director of the Girls as Citizen Scientist Program, which provides the opportunity for girls in Forsyth County to explore the connections between environmental health and public health. So you are both very welcome. Thank you for being part of this amazing event. We are so happy to have you. And so let's start with Dr. Di Vittorio.
Wonderful. Thank you, Luisa. Hope you're enjoying North Carolina, even though it's been pretty cold today. It's usually warm.
It's freezing, but yeah, it's a nice day.
Hopefully you all can see my screen, and I'll enter presentation mode if Zoom doesn't freak out. There we go. Can you all see the screen?
Yep.
Yeah,
looks great.
Perfect. Okay, great. Well, good morning. It's still morning. Thank you, everyone, for the opportunity to present at this meeting. Definitely a new group that I didn't know about before, so excited to stay in touch. So yeah, as Luisa mentioned, I'm going to talk to you about a current research project that's highly collaborative and ongoing on developing a low-cost water quality monitoring system for North Carolina lakes. And so I'll talk about ongoing nutrient management in the Yadkin River Basin, which really motivated this project. Give you a little bit of background on how we can use remote sensing satellite-based data for monitoring water quality. And we'll talk about how I've used some historical data to look at both turbidity and suspended solids and the new data we're collecting to map chlorophyll, and then demonstrate some of the data visualization and analysis tools that we're developing. And then Dr. Kyana Young is teaching today. And so I have a pre-recorded video to share with you to talk about her outreach program that's related to this project and the Girls as Citizen Scientists program. So High Rock Lake, it's about 45 minutes from the Wake Forest campus, making it pretty convenient for me to study. But it's also been a really interesting lake to study from the standpoint of the nutrient management going on right now. And so here is where the lake is within the Yadkin PD. And then the zoomed in view shows the water quality impairments, including chlorophyll, pH, and turbidity. And so the lake was first listed as impaired in 2003. And that's around the time that the Yadkin PD River Basin Association formed, and they've been really critical to driving this nutrient management planning process that has been going on now for over 20 years. So with support from the state and the EPA, there was this model development and calibration period from about 2006 up until about 2016. And so because the lake was impaired, they had to develop a nutrient improvement plan, and they wanted to develop a coupled hydrologic and hydraulic model for this watershed that could simulate nutrient and sediment loads across the watershed and feed that into a hydrodynamic model that can then simulate the water quality in a very detailed way and a 3D gridded structure. And so they had to collect a lot of data to develop and calibrate this model. So there's a really rich data set from the 2005 to 2010 period. It took a while to finalize the model because during this process they decided to revisit the chlorophyll criteria in the lake. So there's the statewide criterion of 40 micrograms per liter, but they piloted High Rock Lake as an area to test out a site-specific standard. And so they settled on 35 micrograms per liter as a new standard, and I'll come back to that again in a few more slides. But really the end product from this model is they could develop these target reduction curves based on the targeted chlorophyll values in the lake. So they could look at the extent to which they need to reduce phosphorus and nitrogen across the watershed. So for instance, if you're using these curves to look at reducing chlorophyll to the 35 microgram per liter minimum, you can find that a phosphorus reduction of about 37% and 27% reduction of nitrogen should achieve that goal based on their process-based model. There were some limitations to the process-based model that the stakeholders expressed, including it has a pretty simplified representation of agriculture. The land cover maps they used were from 2010, which some people consider a bit outdated. Also had a pretty poor representation of sediment loads. However, this was what they produced. They eventually agreed to it in 2016. And so now they're using this model in the nutrient management planning process. And so this started in 2021 and hopefully will kind of conclude over the next few years. It's led by Joey Hester from the NCDWR, and I'm not fully engaged in this process, but there's 4 technical working groups, 1 in ag, 1 in stormwater, 1 in wastewater, and then 1 in stream buffer. And so they don't necessarily regulate all of these different areas, but they're hoping that through this stakeholder-driven process that everyone can kind of come together and collectively figure out a way to get to those targeted phosphorus and nitrogen reductions. And so I was, excited to start looking at, the water quality in this lake because there is an ongoing rulemaking process. So I thought it would be a great time to demonstrate the use of satellite information. And so revisiting the chlorophyll criteria that they developed, one of the pain points on that is the way it's written. They need to assess the lake once in every 3 years, but the state is currently sampling the lake once in every 5 years. So there's sort of a disconnect there, and that we don't really have enough monitoring in place to really evaluate that criteria in a holistic way. Also, they plan on assessing the lake using 1 sampling location. So this Yadkin 152C, which does have high chlorophyll values, but again, that's 1 location across the entire lake. And so I think this is a great example of where satellite-based information can be used to augment and complement the in situ data that they're collecting. So I want to emphasize that satellite data shouldn't replace in situ data, but it's a nice way to expand the amount of information you can get in space and time. And I'll show you some examples of that. So how can you use satellites to measure water quality? So these are some pictures I've taken when I've been out at High Rock Lake. And in the upper reach, it's basically the Yadkin River, and it gets very brown and muddy. And I think most of us have this intuition that if the water looks brown, it probably has high turbidity and suspended solids. Similarly, if you see a section of the lake that's really green, then it probably has high chlorophyll. Well, satellites are basically using the color of the water to infer the water quality. There is quite a bit of physics involved that you need to think about when you're kind of developing the methodology, and I'll try to just broadly explain it here. And so satellites, they orbit the Earth and they take images of the land cover. I'm mostly working with Sentinel-2, which has a revisit period of every 3 to 5 days. And then Landsat, if you combine 8 and 9, you get a revisit period of about every 8 days. So you're getting frequent coverage of the lake or any water body, and it's free to download and process. And so the satellites, they measure the amount of radiance reflected off of the Earth's surface. And the idea is we can take that magnitude of radiance reflected and back into the water quality. It gets a little bit complicated for looking at water because there's a lot of interaction of the radiation in the atmosphere that you have to first take out before you can do much with the data. And then once you atmospherically correct it, you then have to consider the amount of radiation coming out of that water surface that is reflected directly off the water surface or is actually interacting with different particulates in the water. So the radiation that does go into the water, it interacts with different particles and it can scatter in different directions. And some of it should scatter back out of the water surface. And that's what we're trying to measure with the satellite data. I have over here on the right an illustration of what we call in situ radiometry. So when you're developing these methods, it's helpful to have in situ point-based measurements of what's coming off of the water surface, so you can evaluate how well you're pre-processing your satellite imagery. But the main concept is we're getting some measure of what's reflected off the water surface, and we can sort of back into different concentrations of water quality parameters. And so the workflow, so the physics gets complicated, but there's a lot of algorithms that are already out there that are fairly easy to use and apply. And so once you have gathered your satellite image and corrected it, ideally you have what I call matchups. So you have concurrent samples that were collected that have been analyzed in a lab for chlorophyll A, suspended solids, or turbidity. And then it becomes just kind of a regression analysis where you're looking at the magnitude of the reflectance of the satellite image once it's been processed against the in situ water quality. And then once you have that relationship, you can apply it into an entire image and map the water quality across the lake. So this is an example image from the Sentinel-2 satellite, which has a 20-meter spatial resolution. And this was one of the initial models that we developed for chlorophyll, which we've refined, but this is what the final map might look like for a single image. So well, we've been collecting some data to map chlorophyll, but I wanted to start the dialogue with some of our stakeholders, including the Wikipedia River Basin Association, which is comprised of a lot of different members from representing different entities. And so we started with this really rich historical database that they have from 2005 to 2010, because we could find a good number of satellite-based matchups. We also have these process-based model simulations that we can compare the data to say, well, what does the satellite reflectance say compared to the in situ data, but also the process-based model, so we can compare the satellite estimates to other tools that the stakeholders are already working with. And so because we were looking at the 2005 to 2010 period, we were restricted to Landsat 7, which did have this error with one of the sensors. So there's some missing data, but in the stripes you see, but there's still a lot of data available. And Landsat 7 is not great at chlorophyll, but it can give us an estimate of turbidity and suspended solids. So that's where we started, just to sort of pilot how this information could be used. And so here's the fitted regression model between turbidity and the Landsat red band. We have pretty good performance metrics based on our matchups. And then here it is for suspended solids, a bit more variability in the data. However, when we compared this to the accuracy, the reported root mean square error for the process-based model, we had about 1/5 of the error. So even though there is some variability in our analysis compared to the process-based model, we're doing pretty well in terms of accuracy. So here's how you can then apply the model to a full satellite image to map turbidity across the lake. And then we just sort of demonstrate, and this has been published in a paper in the Journal of American Water Resources that I can share with anyone who's interested. We show how you can use the satellite images and to plot time series at individual points. So here I'm comparing the model data to the satellite and the in situ. And you can see where this model limitation was, where it systematically kind of over predicts the peaks and under predicts the ambient conditions, versus the satellite in situ. They tend to align much more closely. And you can see where the satellite data is sort of filling some of the gaps in the in situ database where we don't have any other observations. We also looked at aggregating over, on a monthly scale. And again, the satellite and in situ data tend to align more closely, and there's a lot more variability in the model results. If you aggregate over all of the stations over the full time series, again, you see the monthly means are pretty close. And so we're capturing the seasonality of the suspended solids. Also, you see the error bars there show that there's a much lower confidence interval for the satellite-based observations. You can use satellite data to extend your data set in time. So then we took all of the Landsat imagery from 2000 to 2000 to present. Basically, Landsat 7 was amazing. It was orbiting for over 2 decades. And so you can fill some of these temporal gaps and look at the, you could either look at the averages over the lake. Here we looked at the geomean. You can look at the percentage of time that it's exceeding, or the percentage of the lake that's exceeding a threshold. So the 25 NTU turbidity threshold. This bottom here, I'm showing frequency curves. So often a lot of the in situ data is summarized as a probability of exceedance. So look at, how often or how likely are we to exceed these thresholds. And what I'm showing here is if you only look at dates where we have where we had in situ data, you get one curve. With satellite data, you can extrapolate that in time, which is shown in the green line. So this is looking at all the stations over a full time period. And you see that the curve shifts to the right, showing that we're exceeding it more often. But then if you extrapolate in space and include the full lake area, it shifts down, showing that we're exceeding this threshold less often. So it just kind of shows like how, the extent to which we're the spatial and temporal frequency of your in situ data can affect these decision-making metrics, such as the frequency of exceedance. And so that's, what we did with the historical data. We have a grant from the North Carolina Attorney General's office, and it's been really fun to continue this work and collect new data. And there's several people working on this. So myself, Dr. Kyana Young, who's leading the lab analysis of our samples and doing the outreach. And then Dr. Leila Hashimi-Beni is at NCA&T. And Dr. Chris Zarzar is affiliated with North Carolina Central University, now works for a private company, but they've been working on the collecting drone data. So we're also collecting drone imagery of the lake to what extent can we map water quality with drone imagery, and developing an ArcGIS data portal. So I'll talk a little bit about the chlorophyll maps that we've been developing. And so it's been really fun to go out and collect data. I've been bringing a lot of different students with me. We get to hang out on a boat, which is how I draw them in to do research with me. You can see this, I had a high school intern that was working with me this summer holding the Secchi disc there. Aiden and Michael on the right have been helping with the drone image collection. And then that's Edgar Miller, the Yadkin River keeper in the bottom right, holding our in situ radiometer. So it's actually a pretty easy to use device. And so I can kind of do on the job training with a lot of this equipment, and anybody can come and join us. So if anyone wants to join us on the lake, let me know, although we just wrapped up sampling for this year. So that little device you see, it has 3 sensors on it that measures the incoming radiation from the sun. And then it has 2 cameras angled towards the water and sort of towards the sky to measure what's coming out of the water surface and what's being reflected around in the sky. And you can combine those 3 sensors to back into remote sensing reflectance that can be related to what the satellite signal should be. And these plots just show how that signal from the radiometer that shows the reflectance at different wavelengths at a really high resolution, how it changes with increasing levels of chlorophyll and suspended sediment. So then we aggregate that data to the same band wavelengths that the satellite uses, so Sentinel-2, and we can sort of compare, how well we're matching the satellite-based reflectance to what our in situ device is reading, and we get pretty good relationships here that we were pretty happy with. So then you have your different individual band reflectances. You can combine those to get indices that are related to chlorophyll levels. So now we're using a satellite-based index that measures chlorophyll to our in situ lab samples. And these are 2 different atmospheric correction algorithms that we're playing with right now because we're trying to see which one works best. And you see there's a lot more scatter. So this looks pretty rough, like our squared value is, below 0.5. However, we're pretty happy with where we got, and we don't fully expect our satellite-based estimates to match the in situ chlorophyll. Part of that is, there's a lot of uncertainty in lab-based estimates of chlorophyll. I've read reports from the NCDWR that kind of compare different lab protocols. The other big thing is that there's a big difference in spatial resolution. So we're using, it's good practice to kind of average across use a 3x3 grid of pixels from satellite images. And so we're using like an 80 meter by 80 meter region and comparing it to a single grab sample. So it's really important to emphasize with this data that it's not meant to exactly match your in situ data, but it's sort of an alternative measure. And the goal is that your models are not biased. So they're not systematically like over predicting or under predicting, but they're giving you a much more holistic and synoptic view of the water quality over space and time. So with that, I'll demo some of the water quality maps that we've produced. And I'm going to start with Google Earth Engine. So Google Earth Engine is a really cool tool because you can instantly access a lot of satellite data and do some really quick processing. So one of our atmospheric correction algorithms we can do within this interface and quickly map the water quality. So I've had a master's student working on this. This is his 2nd year, and developed this tool that we're still refining. And so here is a map of like the satellite red band that we're getting from Sentinel-2. And so this is still a work in progress. So we want to turn this into like a final application, but you can see this is where we're still developing the code and the output. But I want to show you some of our initial visualizations. So we can create videos that map the chlorophyll over time. When it looks all blue, it's because sometimes there's clouds. And yeah, I think we still need it's a work in progress. So that's not an accurate map. But this is pretty interesting. We can quickly grab all the historical satellite imagery and map plot time series at either points within. So this is at our monitoring station 152C. We can also, draw a polygon around the section of the lake. So this is the top section of the lake, and plot the chlorophyll over time and sort of see how this time series changes based on different sections of the lake. And so we're working with Mark Vanderborg at the NCDWR to get some feedback on this and how it could be useful to him. But if anybody else has input into kind of the final visualization, we'd be happy to chat with you. We're also working on an ArcGIS data portal. And so here, again, a work in progress. You can see there's some data source errors here with our CAFO data set, but we're trying to compile all of our data into the ARC interface, which is, probably people are more familiar with than Earth Engine. So you can click on here and see these are all the field sampling campaigns that we've done. We have all of our data loaded into this interface. And then the idea is to include other data sets such as like CAFOs and, land cover data sets too, so people can kind of also look at the water quality on a watershed scale. And then finally, I want to, couldn't see with the Zoom bar, mention I worked with a former student, now alum at Wake, who was working part-time for me and part-time with the Yadkin River Keepers. And then she had a fellowship through Winston-Salem State Spatial Justice Studio. And she created, along with a colleague, Grace Fuchs, who was also working with the Yadkin River Keepers, a map for them or story map that looks at different environmental justice issues across the lake, or sorry, across the Yadkin PD Basin. And so I think we also want to integrate some of the data and maps into a story map that can be used to interact more on the community level. And that kind of is a nice bridge to the video I'm about to show you from Dr. Kyana Young, who's doing outreach with young girls and trying to inspire citizen scientists and people kind of feeling collecting their own data and taking part in this advocacy towards improving water quality. So plan is to, I'll stop sharing just for a minute. I'll start the video up and then we should still have time for questions at the end. Let me get this going. I hope this plays. Let me know if y'all can hear the sound.
Greetings, everyone, and thank you for the opportunity to present to you.
Yes,
Perfect. Thank you.
To share some information regarding
it's a little low volume, but we can turn it up on our.
Okay.
So a complementary and
I think I have it all here. I'll turn it up here.
goal of the research project is to enhance this ongoing education and outreach initiatives that have this long-term support from schools within Forsyth County here in North Carolina and the city of Winston-Salem. So we believe that this citizen science participation is a key component of ensuring that those who are interested in invested members of the community can engage in science activities directly related to their respective community and neighborhoods. So the Girls of Citizen Scientists program specifically is a program that engages elementary and middle school girls to address and provide solutions to environmental and community health issues. The program is designed to build this STEM knowledge and STEM skills, to develop a sense of advocacy and activism to address these community health needs and to advance educational and citizen science to positively change and promote health within our respective community. So we designed the program so that the participants will engage in the practice of translational science, translational citizen science, through our scheduled activities with the girls. So again, the program engages girls in this authentic learning experience that promotes this critical thinking and supplements that with this interactive environment that builds, yes, academic skills and confidence, and also the ability to work in teams. Some of the areas that the girls explore include working with creating water monitoring apps, designing and building these robots that will assist in this environmental sampling. They do some light programming, like learning of these programming languages, and they use advanced lab tools to collect and analyze environmental data from the physical world. And there's also a component where they're working in a lab with me at Wake Forest University to analyze the data in the laboratory setting. And the overall goal is that the program will impact the girls' knowledge of and their attitudes about environmental issues and how the environmental issues impacts community health, We want to engage them in this scientific methodology and the practice of scientific methodology. And we aim to also involve parents and community leaders and other professionals from the environmental and health organizations as they're learning about some of these challenges and as they're working toward developing some of these solutions. So specifically, we designed the program to be a 6-session program, and it's centered around these established monthly sampling events. And each session is an academic semester. So the participants are supervised by myself. And if they are available, a Wake Forest University student, and a couple of times we've had participants from Yadkin Riverkeeper join as well. And the participants, they're encouraged to attend the sampling events with an adult in their household, although it's not required, but we have had a couple adults, parents or guardians attend 1 or 2 of those sampling events. And that's really just to create a supportive environment at home as well, in terms of the girls attaining this information and these experiences as they're developing their STEM identity. So for example, in terms of these sessions, 1 month will be dedicated to involving the training of the participants so that they're comfortable and confident regarding what they're expected to do once they are out in the field. So we make over lab safety protocol, sampling protocol, and what the goal of their participation is. So their deliverables. So a lab report, community presentation, actually sharing the things that they've learned. We typically meet at Wake Downtown, so we have a briefing of what we're going to do that day, a briefing of the sampling location, the sampling protocol, and the timeline before we arrive at a sampling location. So the next months, like 2 through 5, they're really looking at just reviewing what we're actually doing and having the girls ask any questions, any points of clarity that are needed, so that we can have a successful sampling event. At the end of the sampling event, the girls return with me to the lab at Wake Forest University, my water engineering lab, to conduct these laboratory analysis of collected water samples, where we quantify concentrations of nitrate, orthophosphate. Sometimes we are able to collect water and send it to the lab on Ronaldo campus for Wake Forest University, where we're able to detect, or we're able to analyze for heavy metals. The girls are also quite familiar and comfortable with testing for the bacteria. This is a fan favorite, I should say, testing for the total coliforms and the E. coli, and they also have experience with sampling for and analyzing the water for total suspended solids and total dissolved solids. And so this is how these sampling events typically occur. We were able to expand the Girls of Citizen Scientists program to include a 2-week summer session. And with this 2-week summer sessions, the girls are in the camp or in the summer camp for 7 hours during the summer. For those 2 weeks, they're learning about the results from the previous sampling events, some of the things that they've noticed as they're going out and monitoring over a period of time, some of their interests that they have now that they have this information, and how they would like their continued contribution to be after participating in the monthly sampling events and in the summer program. I've also had the opportunity to apply for and was awarded additional funding to keep this program going. So we appreciate the support from the Environmental Enhancement Grant to get this started. And at the conclusion of that, we'll be able to continue with the programming for the next 2 years with another external support by the School of Medicine at Wake Forest University. So I do want to thank you all for allowing for me to present today. And now I'll turn the floor back over to Dr. Di Vittorio. Thank you.
Awesome. All right, so do we have I guess I can get the chat open here for questions.
Great. Yeah, thank you so much. Wonderful presentation and really interesting what's going on. And I'm sure if Luisa and I are going to ask some questions, there's one that's posted in the chat. And I'll let Luisa take the first one.
Yeah, of course. Thank you again. It was really interesting. Personally, I didn't know like how to like all these images that you can take from the space to be able to measure the water quality. So for me, that's very interesting. The first question that we have is what kind of drone was used to collect the data, and what kind of imaginary was the drone collecting?
Yeah, wonderful. So I am not the drone person, but the ideal sensor that we would like to use comes from MicaSense. It's the MicaSense red edge that aligns with Sentinel-2 imagery. And so for chlorophyll in particular, it's really helpful to have sort of the red to near infrared range. However, if you just wanted to do like turbidity and suspended solids, the red band alone is good. So you could just use an RGB camera. Of course, there's different, signal to noise ratios. There's different quality of sensors. So the higher, the better, the higher signal to noise, the better. A big challenge we're having though is the mosaicing, because when you're over an open water body, it doesn't have a shoreline to help stitch it together. And we're trying to make this affordable. And so we're using drone systems that cost under, ideally we want to use systems that cost under $25,000. That's sort of the target we set. But we're kind of restricted to the shoreline areas right now to do the mosaicing without going into the really expensive drones that have the onboard GP or RTK. I'm not a drone person, but I'm learning some of the terminology. So I don't know if that helps answer the question. If you had more detail behind that, I'm happy to expand if I can.
Thanks. And perhaps that person will follow up. Go ahead. I'm sorry, Luisa.
No, yeah, I was about to say the same, that maybe the person who wrote the question would like to get more details about it, because the answer was very interesting. So I'm just asking.
Okay.
And there's a follow-up question from Kelly that's on drone. We'll get back to Serena's question in a moment, but is there drone training, or does it take a drone specialist to partner?
I know my students went out on Halloween, which was a gross day, but it was like very perfectly overcast, which gave us good imagery. And they were flying it with the remote control with the main guy who does the drones, Chris Darzar, he has his pilot's license. But yeah, I think it's mostly about getting the right drone fitted to the right sensor and getting it set up right. But it's not like you need to be, specialized. It's the way you'd fly any other drone. It's just it has different cameras on it. And then I saw the sensor is the MicaSense. I don't know if you're familiar with that one. I think though they've been like on and off with producing it. I think that's always a challenge, is the companies change and the sensors change, but I know we were using the MicaSense.
Excellent.
Great. And also, John says that if you could repeat which sensor was used in the drone.
Yeah, I think I answered that one just now.
And I'll just follow up with Serena asks, thanks for the very interesting presentation. 2 questions. Is the modeling you presented in a place that it could be easily replicated in other areas, or is it specific to High Rock Lake? I'll start there, and then we'll come back to Serena's second question.
Yeah, great. Yeah, the same process could be replicated at other lakes. One of the things we're sort of exploring with all this data is how important is it to have that in situ radiometric calibration? And I think the answer we're leaning towards is not that important. And so that kind of, if you can sort of bypass that piece of of like really kind of fine tuning your atmospheric correction algorithm, you can just go straight from satellite imagery to in situ samples and find the matchups and just fit a regression equation. So yeah, this could easily be applied to other lakes in North Carolina. And that was the idea. The grant title was North Carolina lakes in general, because while we were piloting in High Rock Lake, we were thinking like, what's the most efficient way to produce this? We understand the science behind it and the limitations and want to communicate that because that's really important. But yeah, I think, we want to expand this and keep going and apply it to other lakes. And I've looked at different lakes across the state, and a lot of them have the similar pattern where, the upper reach is very turbid and then it kind of settles out, and then you get higher chlorophyll towards the bottom of the lake. So I think too, just the characteristics of this lake, of High Rock Lake, are similar to other lakes in North Carolina. So we could certainly replicate this. I guess the challenge is like going through and finding the matchup data, because the sampling, currently doesn't align with satellite observations. And so while you think you have a really big in situ database, then when you go and filter out all the points that don't have a same day satellite overpass, and then you have to think about clouds, cloud shadows. So it really distills down your data set. So it just, then you just don't have a ton of data to like do a proper calibration validation. But, even if like you're not that confident in how well your model matches your lab data, you could still just use this data to look at trends over time, compare like different areas of the lake, look at hot spots. So even if you're not using it to get like an actual chlorophyll estimate, I think there's still a lot of opportunity in just looking at trends in space and time.
Thank you. That's great. And Serena also follows up with the question, is in examining environmental injustice within the Yadkin River Basin story map and information on the research you provided available to the public?
Yes.
If so, could you provide a link?
Absolutely. I will pop that in the chat. I guess maybe I should stop screen sharing. I didn't know if you wanted to look at the slides, but I'll put it in here. And so that I had very little involvement. That was mainly Bailey Hill, Grace Fuchs, and then the Spatial Justice Studio at Winston-Salem State University. I helped get it started, but really they did all the work. But it's a really cool thing to build on. And I know they want to keep developing it, but time.
Are there other questions coming in? I have a naive question that I want to ask. And I'm wondering about when you're using the Sentinel-2 satellite data, when you talk about it revisiting every 5 days, does that mean there's a 5-day gap in between readings? And if so, are there phenomena like turbidity that might appear and disappear in that time frame and never show up?
Yeah, I mean, you can certainly miss some of these events, and I guess it depends on where your lake is located, but it's usually 3 to 5 days. But yeah, it's not continuous monitoring, although we're testing new satellites. There's a new geostationary satellite that's going up that is going to sort of monitor the Gulf Coast more, but the same, depending on if they decide to do more of these missions where geostationary means it's like looking at the same place continuously. So I think the future of remote sensing, it's just getting better and better in terms of the sensors and the type of data that we're going to get.
Excellent. Thank you. Thank you very much. Well, I will say thank you from everyone that you shared all of this with us. It was really interesting and something hopefully many people can mimic or put into use in their own watersheds, in their own lakes, and in other bodies of water. And we are now we're going to cheer and thank you. You can hear them loudly.
Right.
Yes, and now we get a longer break. We're going to have not only 15 minutes, but also a whole hour and 15 minutes because we get a lunch break. And when we come back at 1 o'clock, you'll meet Renee Fortner, Tim Ormond, and me talking about innovative stormwater management in steep slopes on private property in Asheville, North Carolina. So thanks again very much to both you, Courtney, and your partner, Dr. Young, and that was fascinating.
Yeah, thank you so much for having me.